Hello and welcome to this module on photodetectors. So, we will continue the discussion from the previous module. Here we will look into the structure of a Pn and Apd diodes, okay, avalanche photodiodes for photodetection. This is a schematic of Pin photodiode. So, you see that light is entering from the P side. Of course, sometimes light can also enter from the N region, depending on how you construct whichever is the base material for you or the substrate for you. But the important thing that you have to note down here is that there is a large I section. Now, if you just refresh the terminology of semiconductors, P stands for p-type semiconductor, which means that it is composed of a pentavalent atoms. So, the intrinsic one is the one where you have equal number of holes and the electrons, therefore, there is no net charge out there, whereas P is the one which has been doped with materials called as acceptor ions, right. So, they will actually, if silicon is the material to which you have doped, then 3 of the silicon valence electrons are satisfied, right, and then there would be one hole that is remaining, or maybe it is actually the 5 valence electrons which are donated, one hole will be remaining. For the N type material, you are actually doping them with what is called as donors. In the donors, you will supply them with 5 valence electrons and 1 valence electron will be available for each donors, right. So, P region is the one which is positive excess carrier. So, these are the holes which it carries, whereas N carries largely a negative electrons because it is contributed by the donor ions which give rise to 1 valence electron. The intrinsic region is the one which is kind of neutral, although in a Pin photodetector that is normally used in the detector designs or photodetector designs, it will be slightly P region, okay. It would be slightly P region, okay. The slight P-ness comes because of the doping impurities, or sometimes it is just internally added in order to manage the electric field, okay. If you look at what materials are used for this Pin structure, you can see that there are various materials that are used, right. Each of these materials by themselves can be used for the photodiode circuit, okay. Each of these materials can be used for the photodiode circuits. What you have to see is that these materials are for the intrinsic region I am talking about, okay, intrinsic and the P and N covering regions which I am talking about. What is interesting about these materials is that each of these materials have a large absorption, right. So, on the y axis we have plotted an absorption coefficient in 1 per centimeter, and here on the x axis is the wavelength axis. So, if you look at this absorption coefficient, it is actually pretty large. For example, for silica, which I am showing over here, you can see my pen movement there, the absorption coefficient is pretty large, and then at certain value of the wavelength it kind of abruptly drops down to 0, okay. That same characteristic you can observe for any of the materials. For example, this indium gallium arsenide, if you look at, which is shown in the red, there is a large absorption coefficient, okay, and then suddenly there is a drop towards 0. The sudden drop is not nicely shown here, but there is actually a almost sudden drop there, okay. The same characteristic holds for indium gallium arsenide P material, the same thing holds for gallium arsenide, the same thing also holds for germanium. Now, one sad part of this curve is that silicon cuts off at 1 microns. So, I cannot really use silicon as a photodetector material for the optical communication systems. Why? Because remember, most optical communication systems are operating in the conventional C band and the L band, which means they are operating from 1.55 micron, right. So, they are operating in this region where you can either use germanium, but it is not very efficient, or you can combine this indium gallium arsenide and indium phosphate in order to form a heterostructure, or you can straight up use an indium gallium arsenide or an indium gallium arsenide and P material, okay. So, in-gas P photodiodes or an in-gas photodiodes, or the combination of in-gas and in-P photodiodes, right. The sad part is that I cannot use silicon, and as we know, silicon is the one which is found in VLSI, has lot of this fabrication, nice properties for fabrication. Unfortunately, they cannot be used for optical communication photodetectors. However, there is a recent trend of trying silicon photonics, not for detectors but for other materials. People are working on that. So, hopefully we will be able to harness all of the VLSI technology in order to come up with silicon materials for optical detection as well in future. Anyway, so for now what we are looking at is a structure called Pin structure, right. when light is incident on this one, this is one way of incidenting light, right? There can also be a top level incident. So you put light from the top so that it directly reaches the intrinsic region. What is the characteristic of this Pn diode that I have drawn here? Look at where the biasing is. If you look at the bias is in such a way that there is a depletion layer in the intrinsic region. The amount of depletion layer actually starts to increase as you increase the reverse bias voltage, correct. So, as the reverse bias voltage, the amount of depletion region also increases. What happens during depletion is that due to this negative polarity, the holes which are present here, which are carrying positive charges, these holes would be attracted and then go to the, so this hole actually gets attracted and then flows through the battery terminal. Okay. Similarly, the electrons in the N region will also be absorbed and will flow through the battery terminal, giving rise to a conventional current from this direction. This would be the photo current that I am obtaining, okay, in the direction of this one, right. So, but while these holes and electrons move in this particular way, what happens is that they will leave behind opposite charge carriers. Okay. These opposite charge carriers are immobile, they start extending into the region, okay, because they are looking at this side. So, they start extending into region wherein they will create opposite charges in this way. So, there will be immobile ions layers which are created. To balance out them, there will be positive charges over the intrinsic region, right. In fact, you can see that this extends if you dope the p side with a very large dopant concentration, then this region actually extends into the I region. The amount of charges required in order to neutralize the immobile ions on the p side will be much larger on the intrinsic region. A same thing will happen on this side as well. So, there will be these positive charges, right, which are left behind after all the electrons have moved out. In order to balance them out, you will need a negative charges. And it so happens that if you choose the doping profiles in a way that normally is chosen, you will actually end up having a net number of charges in the I region to be much larger than the plus regions. Okay. So, if you look at the charge density, let me draw the charge density for you. This you can consider it to be some x equal to 0, and then this would be some x equal to something. The depletion layer width from the p side, let us call this as WdP. The depletion layer from the N side, let us call this as WdN. P stands for p type, N stands for N type, right. In between, let us call this as Wi. Wi is the intrinsic layer, right. The charge concentration, if you were to draw, you will see that the p side region is characterized by heavy negative charges. Okay. This is characterized by negative charges because all the electrons that are there, all the holes that are there, they have flown through, only the electrons are left behind. Similarly, for the N type region, you will actually see a positive charges. Okay. So, you will typically see this is the doping profile, N is much more doped compared to the p side region. Therefore, the amount of charges which the N layer covers will be much larger than this one. Okay. So, this would be the charge concentration here. In between, there is a small negative channel kind of a thing, right. It is not exactly a channel, but it has negative charges. Okay. So, this is essentially the charge density rho measured in per coulomb meter, you can say. So, this is a charge density as a function of the cross section or the length along the photodetector. Now, while this is charge density, how about the electric field? How can you find the electric field from the charge density? Well, you can use those Poisson's and Laplace's equations. Here it is the Poisson's equation that you are using. You know that del square V is equal to minus rho V by epsilon, epsilon being the material permittivity of the semiconductor, whatever that we have used, and del square in this case really reduces to d square by dx square because variation is only in one axis. Okay. We also know that this is the same thing. So, we also know that electric field is given by minus dV by dx in this particular case. Why? Because this is gradient of V, right, but gradient minus gradient of V, but gradient in this particular case is a one dimensional function. So, this is simply minus dV by dx, right. This is the electric field in appropriate direction there. So, you can use this equation dE by dx, substituting over here into this equation, the electric field equation. You can see that dE by dx is given by rho V by epsilon. Incidentally, this is one dimensional Gauss's law as well. Okay, you can use these equations. What it tells you is that the electric field is basically the charge density divided by epsilon times delta x. So the change in the electric field is delta x times this. So this is essentially the slope in a sense, right. So you multiply the slope by delta x, you are going to get the electric field. Let us not do all those calculations because I am not going to carry those calculations for you. What is interesting is to actually look at what would be the electric field. There, in order to have charge density constant, the electric field has to rise linearly, right. So dE by dx is some constant k, right, is this some constant k, then integrating this one will give you E equal to kx, or E is proportional to kx. So electric field has to change linearly, whereas the charge density in that particular region is constant, and we have assumed that charge density which is constant. So what you see is that the electric field rises, okay, within this region. So let us try to follow the boundaries which we have already drawn. So this is the boundary for the electric field. So the electric field will rise to a very peak value, this let us call this as E max. The amount of this one that it has raised is given by what is the charge density here? The charge density is Q into Nd. This is the donor charge density, right. So Q into Nd, you divide this one by epsilon, you are going to get the slope. So multiply this one by the appropriate number Wd into n, you are going to get the electric field, right. So this would be the electric field that you are going to get at the peak value. Then the electric field actually slightly reduces while it traverses through the depletion layer, because here the charge density is negative, right. We can give that charge density as minus Q Ni divided by epsilon, okay. So because of this negative, the electric field reduces slightly, and then the electric field actually drops off to 0 when it enters into the p-type material. Here the charge density is Q minus Q Na by epsilon. So you multiply this one by Wd into P, that would be the charge density, but which eventually reaches down to 0, okay. So this is the electric field profile that you can see for a simple Pin structure, okay. So any electrons which are generated here or the photons which are generated, they will be moving in the opposite direction, right. So you can see from the figure on the top, if there is a positive electron hole pair that is generated here, then this positive charge will be attracted towards this side, right. So they would be attracted towards the negative terminal, and it would take this particular direction, whereas electrons will be going in the opposite direction, okay. So this is what you see for the electric field, right. And what is interesting is that you can control the amount of maximum electric field by appropriately adjusting the doping profiles, okay. So you have to adjust the doping profiles, and then you can control the amount of the intrinsic layer width, the depletion layer width, by adjusting the bias voltage. It is for this reason that you will also see what is the maximum usable voltage, what is the maximum reverse bias that you can apply to a photodiode, because if you apply more, then the internal electric field will become very large and it might lead to breakdown of the photodiode itself, okay. Now this is for the electric field, all these terms, but what you are probably interested, if you are designing a photodiode circuit, is what would be the current and the voltage characteristic, right. What would be the current and the voltage characteristic? So if you go back to a simple PN junction diode, you already know what the current and voltage characteristic will be, right. So you start typically with some very small dark current, very small negative current, and then the current will be 0, and then it will start slowly to rise, and then eventually it will rise off, right. There is this cut-in voltage on the positive voltage axis. So if you are forward biasing, you are going to get this. This is for the case when there is no illumination. There is no illumination, therefore this current can be thought of as the dark current. What is dark current? What is dark about it? It is simply that there has been no optical input here. But what would happen to this curve when you actually reverse bias and apply certain amount of optical signal? So consider what happens at V is equal to 0. We have short circuited the Pin junction, right. So by short circuited in the external side, we have not kept any potential difference between the two, but there is a depletion layer inside, because there is an inbuilt depletion layer, and I will supply some optical energy which will create electron hole pairs. And these electron hole pairs, because of the inbuilt electric field which is already there, they will move in the opposite directions, causing a certain amount of current. So even with V equal to 0, external voltage applied to 0, you still end up having some amount of current. Okay. So that's why the graph simply moves vertically downwards. So what you see is this type of a graph. Okay. This is of course slightly exaggerated, it's not slightly, it's been exaggerated pretty badly. So what you can see is that the V gamma, the cut-in voltage that you would have seen for the photodiode without any illumination, would actually become larger and larger. At the same time, the reverse current will also keep increasing. Okay. This is the IV characteristic of a photodiode. Okay. Of course, you have to understand that this scale here on the positive is in milliamperes, whereas the scale here is in the microampere case. Okay. One last point about the materials before we move on. We said that if you take a typical material, semiconductor material, which we are looking for the absorption of light, you see that there is a drastic cutoff, right, at some cutoff wavelength lambda c. Any lambda, that is photons of wavelength lambda greater than lambda c, will not be absorbed. This is important, it will not be absorbed. Only those lambda within which have lambda less than lambda c will be absorbed. Why is this? Well, it turns out that if you go to quantum mechanics of the materials that are there, what exactly is this happening is, you come in with a certain photon, okay, a photon comes in and falls onto the photodiode, then it gets absorbed by the atoms in the ground state, okay, thereby promoting a electron or a particular atom onto the upper state. Okay. This can happen only when you consider light energy which is greater than the energy band gap available. Okay. So if it is less, then you will not be able to absorb. So it will not be absorbed, it will simply be transmitted. Then we say that this particular material is transparent. Material is transparent when it cannot be absorbed, right. So you want your Hc by lambda, which is the energy, C by lambda is F, so Hc by lambda is the energy. This energy should be greater than Eg for absorption, right, absorption. So it has to be greater than Eg. Turn around this equation, you can see that Hc by Eg must be greater than lambda, or lambda has to be greater than lambda. So what would happen here? Hc by Eg into lambda is greater than lambda, or lambda has to be less than Hc by Eg, correct. So you can put in the typical values of H, which is that 6.6 into 10 to the power minus 34, and C value you can put in and express Eg in terms of electron volt. So how do you express energy in terms of electron volt? Divide that one by 1.6 into 10 to the power minus 19, that would be the volt of an electron, right. So if it moves through 1 volt, that would be the energy that the electron would gain. So if you express these quantities, then a nice way of remembering this cutoff condition is that lambda has to be 1.24 micron. So did we get this correctly? We want Hc by lambda to be greater than Eg. So you need to have Hc by, okay, alright. So we have obtained this one. So lambda has to be less than 1.24 micron divided by Eg when you express this one in electron volt. Okay. So this is what differentiates between absorption and no absorption. Okay. So we now have looked at the Pin junction diode. A small change into the Pin will give you APD diode. Okay. APD structure, let me first draw this, I won't draw the structure as such, I will simply indicate the layers over here. So it starts off by having a thin P plus region, a large pi region, okay, this is the intrinsic region, but this is mostly and very small amount of P material doped. Okay, so this pi layer is mostly small amount of P layer doped. There would be one more P region, and this is important, there is an N plus region. Okay, N plus is a heavily doped electron, heavily doped with donors which give you electrons. So there is a large number of electrons over here, and this is heavily doped, and this is also typically P plus doped, or at least very highly doped. So you will actually see that there is a large electric field gradient over here, because once this is reverse biased, this will leave behind a lot of positive charge carriers over here, the ions there, and P will be negative. So there is a large gradient of the electric field. Okay. So if you sketch the electric field itself, you will see that a large electric field you are going to get over here, and then there is a drop off of the electric field because this region becomes negative, right. This was simple Pin type of a structure. Of course, it is not N here, but it is just P and I type, and here what will happen is because of this P plus region, okay, so there will also be these holes which will make this fellow negative by a large amount, and the electric field will go down to 0. Okay. If you dope it slightly, or if your reverse bias voltage is not very high, then this electric field gradient will not be very large. Okay. So, it would look something like this. So, this would be the case for low bias situation. Unfortunately, for this situation you will not really get the effect of the multiplication layer, because you need a certain amount of E minimum in order to for the impact ionization to occur, because electric field carries a certain amount of energy, half epsilon E square is the energy that is carried typically. So, unless that energy will be greater than the lattice constant of the material, it will not be able to kick that lattices which are in the absorption in the multiplication region in order to release the secondary EHPs. Okay. To release a secondary EHPs by the impact ionization, you have to kick them very hard, and that can happen only when the electric field is of sufficient value such that there is enough amount of energy to kick them and then generate the secondary EHPs. Because this generates secondary EHPs, the responsivity of an APD is multiplied by a factor called M. M is the multiplication factor. It turns out that this multiplication factor is a statistical parameter. You cannot say that M is equal to 10 or M is equal to 20, or with a predicted value. M can be measured. Okay, it is mostly measured and power fit and curve fitted to find the value of M for a given structure, but you can't in general say that this is the value of M with any nice precision. So, this is slightly statistical parameter. In fact, this shows up in the APD noise as well, which we will see in the next module. We will see that because of this multiplication factor, even the noise kind of becomes large in the APD structures compared to PIN structures. Advantage: larger current gain. Also turns out that this can be made to work very fast, okay. But large current gain is the primary advantage of APDs. Disadvantage is that the signal to noise ratio suffers a little bit, okay. But they are very useful for measuring extremely low optical powers, okay. The responsivity for the APD is M times the responsivity of the Pn diode. So, whatever the quantity that you get as a straight factor of 1 for the APD, it becomes factor of M multiplication, okay. One interesting thing about this one is that typically light enters for an APD in this way. So, it actually enters from the N plus region, okay. Light is incident from this region, and this N plus region is made sufficiently thin so that most of the light is actually coming through to the P region. Again, this P region will also be made in such a way that light does not really get absorbed much there. Now, how can we ensure that it does not happen? I mean, what can we do about that? It turns out that if I use indium phosphate over here, these in-P materials have a band gap of about 1.35 electron volt, which means that for lambda that is greater than around 960 nanometers, okay, this will not be sufficient energy here, right, so that whatever the photons that are incident will not be absorbed here. This P layer and the N plus layer, if you dope them with in-P material or make them with in-P material, they will become transparent to the light in the optical second and third windows. So, light simply goes through the intrinsic region, reaches the pi region or the intrinsic layer where it gets absorbed. How can we ensure that? Well, you operate this one with an in-gas diode, in-gas material. We know that in-gas material has a cutoff at 1.6 microns. Right, or 1.7 microns. So, this will absorb all the photons, right. However, the photon carriers that are generated, the photo carriers that are generated, they will be collected in this region, they will be sent into this region, so that they will experience a very large electric field, and this electric field will then cause them to generate the secondary EHPs. Okay. So, this is how this particular material is performed. Of course, P plus region here also is made up of in-P material. So, if you look at it, you are looking at a sandwich structure where the material, the intrinsic layer is essentially a in-gas material, and the layers on top and bottom are with the different materials. Okay. So, this is how a typical SAM APD works. Sometimes you also find separation, graded absorption, multiplication regions. Okay, so you, instead of making this abrupt, kind of do some grading of the layer in order to obtain even better current gain profiles, okay, and to change the noise properties. So, well, this was all about the structure for APD and structure for Pn diodes. We will then look in the next module about the response time of the photodiode, which essentially is determined by the bandwidth of the photodiode, and we will look at what associated noises are there in the photodiodes, and then we will talk about simple optical receiver. We will go back to the communication system which we talked about in the first or second modules, and then we will talk about that simple direct detection, on off keying detection, okay, and then see what kind of optical receiver trade-offs one has to perform in order to detect optical signals and to make an optical receiver function. Thank you very much.